Hello, class. So in this video, we're going to finish out section 1.3 in the book. We're talking about classification of ODEs. So we can classify them into three different categories: type, ODE versus PDE; order, which is just the highest order derivative you see in the differential equation; and linearity, which was a little bit harder to explain because we had to explain basically in this way, that a differential equation is linear if you can write it like this, in this form. Now, what is this form? Again, what I mentioned is basically you have a derivative, and it's nth order, right? So the highest order derivative should be an nth derivative times some expression involving x or constants plus another derivative, and the coefficient has to be some expression involving either x or constants, where x is the independent variable. Right? Again, derivative, the coefficient has to be some expression involving x and constants. I mentioned that y, you can think of it as a derivative as well, as specifically, you can think of this as that derivative y to the 0, so the 0th derivative. And then finally, anything that doesn't have y's should have only the independent variable or constants. And that's what g of x means. That means there's no y's involved. Now, I mentioned that it's not very easy to see, when something is linear, but I did give you a sort of algorithm to check. And basically that algorithm to check is the same thing I mentioned right now. So we did this example where we went over these differential equations, determining whether each one was linear or not. So let me just do some of these again, just to make it clear. And I'm spending a lot of time on this because most of the time we're going to be working with linear differential equations. Why? Because if you've taken linear algebra, which unfortunately is not a prerequisite for this class, you'll see that a lot of the techniques we're going to use for solving linear differential equations come from the fact that we can think of these as some things called linear transformations. So if you've taken linear algebra, you're going to see a lot of terminology from that class being applied here. Since, again, linear algebra is not a prerequisite, I'll have to go over some things, not as in much detail as I would like, but still in enough detail that we can understand how are things working. Okay, so that's why I'm spending a lot of time in linearity. It's really important. Okay, so we want to go over a process about how to determine whether differential equation is linear, and the process is basically this. So let's say we try problem 2. Right, so t squared times y double prime minus 4 times y prime equals negative sine t. Right, so what's the process? First, look at each derivative. Anytime you find a derivative, focus on that term. Okay, so I look at this expression. Okay, I have a derivative here. It doesn't matter in what order you look at the derivatives. I guess just for sake of having some sort of specified order, I'm going to start with highest order first. Okay, so I see a second derivative. Okay. Look at the coefficient in front of it. If it doesn't have any y's, but only has the independent variable and constants, then that's fine. So here, the independent constant is t. The independent variable is t, sorry. Okay, I can see that there's no y's here. It's only t squared. That's good. Go to the next derivative. Look at the coefficient in front. Do you see any y's or any dependent variables? No. Is all you see constants or expressions involving the independent variable? Yes. Okay, then you're good. Finally, look at everything that is not multiplied by a derivative of y. Is it an expression only involving t's or constants? Yes. Okay, then you're good. This is linear. That's basically what you do. You check each derivative and then check everything else that doesn't have a derivative, that is not multiplied by a derivative. So for example, let me rewrite this one here because there's some writing from before. If we look at number 3, ty y double prime plus 4y y prime equals 0, and we want to check if it's linear, we do the same process. Okay, there's a second order derivative here. What's in front of it should be either an expression only involving t's or constants. Right? Should just be, so not or, should just be an expression only involving t's or constants. If there's any y's, that's bad. Okay, there's only t's or constants, we're good. So another derivative here, look at the coefficient. Now this is a problem because now the coefficient has y's in it. It has a dependent variable in it. As soon as you see that, okay, the differential equation is not linear. It's not linear. It's basically as simple as that. It's a little bit of work because you have to check each term, but eventually you're going to get very good at it and just see something and be able to tell, okay, this is linear and this is not linear. The only other thing that you have to worry about is if you ever see a power of a derivative, not a higher order derivative, but a power of a derivative, then it's not a linear ODE. So if we look at this differential equation, I'm going to write it again. So if we look at the differential equation, y double prime squared plus 3t equals 0, this is not linear because we have a derivative to some power that's not just itself, not just one. Okay? So here I have y double prime to the second power. That means it's not linear. Okay? Another way you can think of it, if you have any sort of products of derivatives, then it's not linear. Because remember, y double prime squared is y double prime plus y double prime. So you can't have powers greater than 1 of derivatives, which is the same thing as saying you can't have products of derivatives with each other. Okay. Now that's how you determine if a differential equation is linear. There's just one more thing to cover, kind of two things, but really just one more thing to cover in this section. It's just notation. Okay. So given an nth order linear ODE, what does that look like? Well, we know a general expression for that. Okay, we know that a linear nth order differential equation has to look like this. It's linear because it has the right form, and it's nth order because the highest derivative is an nth order derivative. Now, if we're saying that this is nth order, then this function can't be 0. Because if this function or expression is 0, this whole thing would be 0, and then this wouldn't be nth order. It would be nth minus 1 order or something less. So we know that this coefficient is not 0, so what we're going to do is divide both sides by this coefficient function, a sub n. So that's all I did in this line here. What I did was divide everything by a sub n. What I'm trying to do is solve for the highest order differential equations. I have it by itself on one side of the equality, have everything else on the other side. Now that I've done this, now I just have to move all of this to the other side. So I'm going to subtract all of that to the other side. And what am I left with? Oh, and there's a typo here. It should be divided by a sub n. So what am I left with? Well, the nth order derivative of y equals g of x divided by a sub n minus this whole other thing, right, that we subtracted from both sides in the previous step. Again, all I'm doing is trying to get the nth order derivative by itself. So it's just basic arithmetic or algebra. Now, what is the goal of this? The goal of this is to introduce this notation. This equation, this expression here, let me just call it star. Oh, that's not a star. I don't know what that is. So this equation here, I can write it as the nth order derivative of y equals some, let me write it like this. Let me use this variable. Phi of x, y, y prime, y double prime, all the way to the f minus 1 derivative. Now, what does this mean? Okay, first of all, phi is a Greek letter. This is just representing a function. Okay. So what am I saying here is sometimes I'm not interested in what this whole messy expression is. Sometimes I'm only interested in what variables are involved in that expression. So I'm not necessarily interested in knowing that it has this exact form, just what variables are involved there. For example, if you look at this part that I underlined in red, what can you see there? Well, you can see the variable x, you can see the variable y, you can see the first derivative of y, the second derivative with respect to y, all the way to the nth minus 1 derivative with respect to y. So a lot of times, someone in the book and in most books, they are going to write something like this as saying, look, I don't care what this expression is. All I care about is what variables are involved and what derivatives of y are involved. So instead of giving you an explicit expression, I'm just going to tell you it's a function of these variables, meaning it's an expression of these variables and these derivatives. Now, phi, it's just a name, so you can call it f. It could be f of this, g of f. oh, I already used G above. Sorry, let's use H. That's what it means. Whenever you see F or H or some variable of all of these, or some, yeah, variable of all of these variables, that means it's just an expression involving those variables. Okay? Now, the reason why I introduced that, well, first, like I mentioned, it's used in the book and in most books as notation. In mathematics, you always try to generalize things as much as you can. Okay, so anytime you can find a general way of writing an expression, you usually do it. And this is a very nice, general, closed way of writing a very messy expression. Now, let me talk about initial value problems. This is the point, one of the other points why I wanted to introduce this notation. So we've kind of talked about initial value problems before, right? I mentioned what initial conditions are and what boundary conditions are in the previous problem. Okay. So here I'm going to define it now more generally. Okay. So suppose we start with the linear ODE. Okay. Now here I say that it works in general. Okay. The point is we want to start with a differential equation that you can somehow rewrite like this. So basically, if you can solve for the highest order derivative, which in this case is the nth derivative, then this notation works. So in the case that the differential equation is linear, I already showed you how to solve in this form, right? Just divide by the leading coefficient and then subtract everything to the other side. If it's not linear, it's fine, as long as you can solve for y, the nth derivative of y with respect to x. Why? Because, again, the goal is to write it in this form. The nth derivative equals something. Okay. So given a differential equation of this form, now you have to go back to what I mentioned a couple of videos ago, that I was talking about how every time you integrate, you get a constant of integration. And if you integrate twice, for example, to find a solution for a differential equation, that's going to give you two different constants of integration, right? Because each time you integrate, you get a new constant. How do you get rid of those constants? Well, you need initial or boundary conditions. And that's the example we worked a couple of videos ago. Now, what that means is if we have an nth order differential equation, we're going to have to integrate n times, right? Because there's n derivatives. We get rid of each derivative by integrating. So nth order derivative means we're going to have to integrate n times. If we integrate n times, that means we get n different constants of integration. So every time you integrate, you get a new one. That's what I mentioned in previous videos. What that means is if you want to get rid of these n different constants of integration, you're going to need n either initial or boundary conditions, or a mix of them. Okay. So in the example where we had, so let me go back to this one. I know I'm using it a lot, but it's just a good one to use. We had this, and actually let me write it in terms of s. So right now it's written in terms of the velocity function. Let me write it in terms of the position function. So velocity is the first derivative of position. So the derivative of velocity is acceleration, which is the second derivative of position with respect to time. So here we had a second order ODE, linear as well. But the important thing is that it's second order. It's already in the right form. We have the higher order derivative by itself. So we know that in order to find a solution, s of t, we're going to have to integrate twice. And if you remember, in this problem, I gave you two conditions. I gave you the condition s of 0 was 100, and then s prime of 0 was 5. Right? Where the s prime velocity was initial velocity, s0 was initial position. Now, I told you this is an initial condition, basically because it affects what the solution functions can be, and because it starts at the start of the experiment, which was time or input equals 0. Here, we were evaluating, yeah, no, these were the ones that we used, right? So in fact, both of these are initial conditions because we're evaluating at t equals 0, sorry. Yeah, so I didn't remember exactly what we did in that example. But both of these are initial conditions. And since we had a second order ODE, we needed two conditions to get rid of the constants of integration. So that is what this paragraph is saying. So now let me go back. So given an nth order differential equation, you're going to need n initial conditions. And it doesn't always have to be this way, but usually they're going to follow this pattern where, okay, we have an nth order derivative. We integrate once, we're left with an nth minus 1 order derivative. So we need a condition of this form. Okay, so we give a condition of that form. Evaluate the nth minus 1 derivative at some value, and you should get another value. Integrate again, you're left with an nth minus 2 order derivative. Again, we want some condition involving that. So again, you give it a condition. Evaluate at some value, and that should be equal to some other value. And you do this all the way up to the original function. If you integrate it an nth order derivative n times, you should get to the original function you're looking for. Again, we want a condition to get rid of that last constant of integration, so we give it. Right? Evaluate at some input, that equals some output. That's the exact same thing that happened in this example. We had a second order derivative. We integrated twice. We're left with the first order derivative. Right? So we needed a condition involving that. Integrate again. We're left with just something involving s, the original function, but we still had a constant of integration, so we have to give another condition to get rid of it. So this is what an initial value problem is. An nth order differential equation with n initial conditions all at the same input. Now, this input doesn't necessarily have to be the start of the experiment. So for example, if x is time, this doesn't have to be time equals 0. A lot of times it is going to be, at time equals 0 or whatever input equals 0 or whatever input the start of the experiment is. It doesn't have to be that way though. For example, if all of these conditions were instead of s of 0 and s prime of 0, they were like s of 1 and s prime of 1, that would still be considered an initial value problem. If those inputs differ, so let me erase this just for space. If the inputs differ, right, so we're not evaluating each of these functions at the same input, so maybe this is not x naught, but some other value, say a naught, then we call this a boundary value problem. So if all the initial conditions are the same in the sense that they're all being evaluated at the same input, the output doesn't matter. As long as they're being evaluated at the same input, it's an initial value problem. If at least one of the inputs is different, it's a boundary value problem. Now, finally, so I guess for sake of time, I was going to do an example here, but I kind of already talked about it in the sense that, this differential equation is second order. Right? It's a second order differential equation where I replaced v with s prime, right? Because velocity is a derivative of position. I guess one thing I can say is, notice that we can get it in the right form. If you divide everything by m, you get negative g plus k over m s prime of t. And if you want to write this more generally, this is where this other notation is useful. You can write just s double prime of t. If you're not interested in specifically what this is, you can just write it as s double prime of t equals some expression involving the input, the function, and this first derivative. You may ask, well, I don't actually see the function or the function s here. So if you want to be more precise, you can say that this is just something, or the independent variable t specifically. I would always include this, but if you want to be more precise, you can say that this is just t and s prime. Usually, just always include the lower order derivatives, even if you don't see them explicitly. So since that is the way it's done, you can write this like this. So again, and some function of this, right? So maybe phi of that. So again, the point of this is sometimes I'm not exactly interested in what this expression is specifically, just what variables and derivatives are involved in it. So that's the last thing in section 1.3. In the next video, I'm going to start on section 2.2. I'm going to be skipping section 2.1, but I'm going to talk about more about that in the next video.